All right, so I've started recording, so everyone who has the mics on, please switch it off. Right, so we are going to look at epicyclic gears. Right, we already covered um, simple and compound gear drives. Right, so now we're going to look at how you would approach problems based on epicyclic gears. Right, now I'm sure you've or you should have watched the video I sent yesterday based on epicyclic gears, right? So now I just want to give you a guidance as to how to approach problems based on epicyclic gears. Right? It's very simple. Right? The approach I'm going to teach you is a simple one. Right? There's actually some form of guidelines that you have to follow. Right? If you follow these guidelines, you should be fine regarding epicyclic gears. That's if epicyclic gears will be in the exam. Right? Now, with epicyclic gears, right, you always have to draw this table. That's number one, right? Now on the table, right, this is where we tabulate any and all our information, right? On the first column, you have the number representing the number of condition, right? The second column is the condition, right? And then you have the apparatus that exist on your epicyclic gear train, right? Now a typical epicyclic gear train will have an arm, right? An analysis gear, a planetary gear, as well as a sun gear, right? Typically, that's how it goes, right? Now, on your table, this is how I like to lay out my gears, right? I have the number of condition, I have the condition, then I have the arm, right? So the first two columns after the condition, right, are going to be based on what I have, right? The apparatus which I included in my first condition, right? So in my first condition, the first condition speaks of the arm and the analysis, right? Hence, on this column, I'll have the arm, and then on the following column, I'll have the analysis, right? Both of which are included in the first condition, right? And then how I arrange my next columns, right, is going to be based on how the gears are meshing on the problem at hand, right? Now, for instance, if you look at this problem, right, you have an analysis, right? So that's the analysis. It's been named as gear A. So gear A is our analysis, right? Meshing with the analysis, you have gear D, which makes this the first planetary gear, right? So you have gear D meshing with the analysis, right? So on my table, after gear A, which is the analysis, I'll have the gear, right? In the following or in the next column, I will have the gear that meshes with the analysis. Right, so now the gear that meshes with the analysis is gear D, right? Hence, I have gear D here, right? Now, it so happens that in this problem, right, the gear that comes after gear D, gear C, is fitted with the same shaft with gear D, meaning that whatever rotational frequency that this is rotating, right, gear C is rotating at the same rotational frequency and going in the same direction, right? So because of that, instead of having two columns representing gear D and gear C, I have both gear D and C under one column, right? But first, I have gear D which meshes with, I have gear D which meshes with gear A, and then I included gear C because essentially C and D are rotating at the same rotational frequency, right? Then the column that follows, right, I have the gear that meshes with gear C. So as you can see here, After gear C, you have gear B, and B meshes with C. Right, so that's how I lay out my gears. I lay them out in terms of how they are meshing. Right, you have the arm, you have the annulus, both of which are part of condition one. Right, after that, the columns that follow. Right, so the column that follows after this, right, I will name as the gear, or I will have the gear that meshes with this gear here, the annulus. Right, then after that, I have the gear that meshes with this one. Right, so that's how I lay out my gears. Right, now in epicyclic gears, right, in tabulating your information, right, what I also like to do is to write down the number of teeth of each of the gears, right, on or at the top of each column. So at the top of this column, I have the number of teeth of gear A, then I have the corresponding number of teeth of gear D, the corresponding number of teeth of gear C, and the corresponding number of teeth of gear B. Right? The reason why I do that is because in order to fill condition one, or in order to complete condition one, you only need one thing. Right? So to complete condition one, you only need the number of teeth, nothing else. Right? If you have all your number of teeth, right, only the number of teeth. If if you have all the number of teeth, right, that is all you need to complete condition one. Right? Again, to complete condition one, all you need is the number of teeth of all your gears. Right? Which in this case they've given us all of the number of teeth. Right? Now, let's get into the conditions on the table. Right? Remember, I mentioned this table you always have to draw. Right? Now let's get into the conditions in the table. Right? Now, as far as conditions, you have condition one and you have condition two. Condition one and two are fixed conditions. Right? By fixed, I mean those are two conditions that never change. Meaning that for condition one will always be fixed arm and rotate the annulus by one revolution clockwise. Right? Now, shorthand notation for one revolution clockwise is by simply saying by positive one. Right? So I was supposed to say here by positive one rev. Right? So shorthand notation for by one revolution clockwise is by simply writing positive one rev. So positive one rev stands for one stands for one revolution clockwise. Right. So the positive one rev stands for one revolution clockwise. So when I say condition one and two are fixed, it means that the first condition we will always fix the arm with whatever, however the arm has been denoted. In this case, the arm has been named arm E, right? Hence, instead of just having fixed arm, we are specific in saying fixed arm E, since we are dealing with arm E. Right? So fixed arm E and rotate the annulus. The annulus here has been labeled as gear A. Hence, instead of just saying annulus, I said and rotate gear A, which is the annulus, by one revolution clockwise. So by positive one rev. Right? So that's the first condition. It remains the same in any and all cases. Right? So then condition two, right, is also fixed, meaning it never changes. So condition two will always be multiply the first condition by x and add y. Right? So you multiply the first condition by x and then add y. Right? So those are the first two conditions which are fixed, which will never change. Right? So in drawing your table, right, you drop your table, right, and then you complete condition one, which will be fixed arm and rotate the annulus by one revolution clockwise. Then you fill condition two, which is multiply by x, essentially meaning multiply first condition by x and add y. right? And then you fill out the rest of the columns, right? Now, when I said the arm and annulus are part of the first condition, this is what I meant, right? In the first condition, what you're trying to get, or what you're trying to do, is to get the rotational frequency of each of the gears, right? If the arm is fixed, if the arm is fixed, it means it's not moving, hence, or it means it is not rotating, hence the arm here is equal to 0, right? Or the rotational frequency of the arm is equal to 0, right? So what you are trying to do with the first condition is you are trying to get the rotational frequency of the other gears if the arm is fixed and the annulus is rotating by 1 revolution clockwise. So this is fixed, hence it's equal to 0. And from condition 1, we are told that this is rotating by 1 revolution clockwise, hence the positive 1. So what is the rotational frequency of gears D, C, and B if the arm is fixed and the annulus has been rotated by 1 revolution clockwise? Again, condition 1, we are trying to get the rotational frequencies of the gears if the arm is fixed and gear A, the annulus, is rotating by 1 revolution clockwise. All right. Now, how do we get the rotational frequencies of each of these gears if the arm is fixed and the annulus is being rotated by 1 revolution clockwise? All right. It's very simple. Right. You follow these guidelines I'm about to tell you. Right. You simply follow these guidelines. Take note of these guidelines. Right. It makes epicyclic gears very easy. Right. Take note of these guidelines because I haven't written them anywhere. Right. So if you have to write them down because they are going to help you. Right. So the way we go about filling condition 1, right? So getting the rotational frequencies of gears D, C, and B, right? Is by using, or is by following the following guidelines, right? So you first identify, right, the relationship between the gears, right? What I mean by that, I mean, right, the reason why I have my gears laid out the way they are, right, is because in filling out the first condition, right, following these guidelines, you first identify the relationship between meshing gears, right? Now, like I said, how I lay out my gears is such that the gears that follows, right, is always meshing with the one that comes before it, right? So you have A, the gear that follows would be a gear that meshes with A, right? And then in this column, we have both D and C, right? Because D and C are fitted with the same shaft, hence rotating at the same rotational frequency, right? But the gear that follows, right, is one that meshes with C, right? So guidelines, identify relationship between meshing gears. Now, what is the relationship between meshing gears, right? There is only one, and that relationship is one of circumferential velocity, right? Circumferential velocity, a general formula for circumferential velocity is pi dn, right? It is pi dn, right? Now, I'm sure I covered this with you guys, but um, just to remind you of this, right? If you have two gears, or if you have gears in mesh, this one is rotating clockwise, and this one is rotating anti-clockwise, right? Where the gears meet, right, at the circumference of where the gears meet, or where the gears meet, you have this linear velocity, right? We have that linear velocity which we know as the circumferential velocity. right? Circumferential velocity, velocity, right? That's V, right? The velocity or the circumferential velocity of gears in mesh is the same, right? So if, for instance, if we take this as gear A and take this as gear B, right? It then means if the circumferential velocities of gears in mesh is the same, it means that VA is equal to VB. So by you first identify the relationship between meshing gears, this is what I mean. This is the only relationship between meshing gears, right? So essentially, the circumferential velocity of meshing gears is the same, right? Now, bearing that in mind, right? Now, this is the general formula for calculating the circumferential velocity, right? For gears specifically, right? The circumferential velocity is equal to pi times, and then instead of diameter, we use what we call the PCD times n, right? Now, guidelines as to how you fill the first condition. You first identify the relationship between the meshing gears, right? So we have filled this column, filled this column. Now it's time to fill this column, right? So what do? We identify the relationship between this gear and this gear, right? Gear A is meshing with gear D, right? Gear A is meshing with gear D. So because those two gears are meshing, it means their circumferential velocities are the same, meaning V, you have D and A. VD, right? The circumferential velocity of gear D is equal to the circumferential velocity of gear A, right? That's the first thing you do, identify the relationship between the two gears, right? Now, I'm going to show you this quickly, right? Now, you do not have to do the following step, right? I'll show you why you do not have to, right? I'll show you where to start or how to, or why you do not need to show what I'm about to show you, right? This is just for interest sake, right? So the circumferential velocity of gear D is equal to the circumferential velocity of gear A because those two gears are meshing, right? So relationship has been identified. That's how you identify the relationship, right? Now, VD is going to be equal to pi times the PCD of gear D times the rotational frequency of gear D is equal to VA, which will be equal to pi times the PCD of gear A times the rotational frequency of gear A, right? Now, the pi is the same, so it cancels, right? Then you have PCD times the rotational frequency, right? Now, as far as the PCD has its own formula. PCD is equal to module times number of teeth, right? So instead of PCD, we use its formula. So the PCD is equal to the module times the number of teeth of gear D times the rotational frequency of D is equal to the module times the number of teeth of A times the rotational frequency of A, right? Now, what you should know by now, right, which we identified even with simple and compound gear drives, right, is the fact that if you have gears in mesh, then their modules has to be the same, right? Gears are able to mesh because their modules are the same. If their modules are not the same, they are not able to mesh, right? So meaning the module are the same, hence it cancels. And then essentially you're only left with ND times TD is equal to NA times TA, right? Now, what I meant by the next step you do not need to show, right? It's this step here, this one. So from here to there, you do not necessarily have to do this every time you do problems based on what is this epicyclic gears, right? This is just for you to understand how we get to this step, right? So identifying the relationship between meshing gears, right, being this means that you are always going to come to this step, right? So this actually tells us that the velocity, right, of each gear can be expressed in terms of just the rotational frequency of the gear and the number of teeth of the gear, right? So meaning when doing the first step, identifying the relationship between the meshing gears, which are the meshing gears. Right now, we're looking at D and A, right? The relationship between those two gears is the fact that the circumferential velocity of both gears is the same, right? So instead of doing this, right, you can simply start your solution at this point, right? So this is how you essentially identify the relationship between the two gears. Are we clear here? Right? So this is how you identify the relationship between the two gears. Right. So first step, you identify the relationship between the two gears. Right. Okay. Excuse me for a moment. I just want to check something here. Okay. Right. So identify the relationship between the two gears. This is just like we have here. This is how you identify the relationship between the two gears. So that's the first step. Second step is, right, the second step is you establish direction of rotation, right? So first step is you identify the relationship between the two gears, which is essentially this here, Vd is equal to Va. Second step, you establish direction of rotation, right? Now, as far as gear A and gear D, right, we know the direction of rotation of gear A, right? We were told from the first condition that gear A, the annulus, is rotating clockwise. So meaning the direction of rotation of gear A has already been identified, is going clockwise, right? Now, like we established when doing simple and compound gear drives, that if you have an annulus and it has teeth on the inside true circumference, whichever gear that meshes with it tends to go in the same direction as it, right? So meaning, as you can see here, the annulus has teeth on the inside true circumference, and the gear that meshes with the annulus, right, is meshing with the annulus using the inside true circumference, meaning that whichever gear that meshes with gear A is going to go in the same direction as gear A. So if gear A is going clockwise, it means gear D is also going clockwise, right? So again, first step, establish the relationship between the two meshing gears, which is this one, Vd is equal to Va. Second, you establish direction of rotation. We've established that this is going clockwise, right? And we also established that whichever gear that meshes with the annulus is going to go in the same direction as the annulus, meaning that gear D is also going clockwise, right? Now, third step is to solve for what you're looking for. We are looking for the rotational frequency of D, right? Remember, condition one, you are trying to establish the rotational frequency as well as direction of rotation of each gear if the arm is fixed and the annulus has been rotated by one revolution clockwise, right? So essentially, you're looking for the rotational frequency, right? So again, as far as guidelines, first thing you do, establish the relationship between the two gears, Vd is equal to Va. Second, you establish direction of rotation. This is going clockwise, that's going clockwise. Third, you solve for what you're looking for. We are looking for ND, So we solve for ND. Hence, we divide both sides by TD. Right? Hence, ND is equal to NA times TA divided by TD. Right? Which is exactly what we have here. So this comes from following these three simple steps. Right? And now you substitute. Right? You already know the rotational frequency of gear A. We were told this has been rotated by 1 revolution clockwise. So that's equal to 1. Number of teeth of A is 100, right? And the number of teeth of D is 16. Then punching that in your calculators, we get 6.25. So if this is fixed, so if the arm is fixed and the annulus is rotated by 1 revolution clockwise, this rotates at 6.25 clockwise. The fact that it's positive means it is rotating clockwise. Right? And then if this is rotating at 6.25, it means this is also rotating at 6.25 because they are fitted with the same shaft. Right? So we filled this column, so we go to gear B. And then we follow the very same guidelines. First thing you do is identify the ratio between the meshing gears. Right? So gear B meshes with C. Hence, we know NB times TB is equal to it measures with C, so NC times TC. Right? Essentially, that is VB is equal to VC. You've established the relationship between the two gears. Next, you establish direction of rotation. Right? Now, gear C is going in the same direction as gear D, remember? So if gear D is going clockwise, it means gear C is also going clockwise. So we've identified or we've established the direction of rotation for gear C, it is going clockwise. Right? Now, if you look here, gears C and B, right, are meshing with the outside true circumference, and gears meshing with the outside true circumference go in different directions. So if gear C is going clockwise, it then means gear B is going anti-clockwise. And the way you represent anti-clockwise is by adding this negative sign here, right? This then means that that's going clockwise and this is going anti-clockwise, right? Remember, first thing you do, establish the relationship between the two gears, VB is equal to VC. Next, you establish direction of rotation. This is going clockwise, meaning that's going anti-clockwise, hence the negative, right? Third step, you solve for what you're looking for. We are looking for NB, therefore we divide both sides by negative TB, right? Therefore, NB is equal to NC is equal to NC times CC divided by negative TB, which is where we got this from. And so this you get by following those three easy steps. So now you substitute, right? NC, remember the rotational frequency of C and D is the same. Hence, since we have ND, we can simply use ND. 6.25. Number of teeth of C is 22, right? Divided by negative TB, right? So negative, and then TB, number of teeth of B is 28. Then you simply punch this in your calculators and you get negative 4,911. And just like that, the first condition is complete. Right, now the first condition, right, in your table is the most important one. If you mess up the first condition, it's pretty much over. If you mess up the first condition, it means all your conditions will be wrong. Right, all your conditions are contingent, right, on the first condition being right. Right, any questions?
So far, so good.
Right, let's move on to the second condition. Right, so second condition is you multiply the first condition by x and you add y. Right, so meaning you're going to multiply condition 1. So 0 times x is 0, then you add y, so you get y. Right? X times 1 is x, then you add y. X times 6,25 is 6,25x, then you add y. X times negative 4,911 is negative 4,911x, then you add y. Second condition complete. Right? Now, conditions that follow after the second condition are based on how many questions you have that are based on the problem you are looking at. Right? Now, if you look at the questions based on the sub questions based on this question or based on this problem, you have 3.1 and 3.2, both of which require us to tabulate information. Right? So this means that this question is going to have its own condition, and this question is going to have its own condition. That means that, as you know, you have the first two being fixed. You have the first two conditions that do not change. So, meaning if you have two more conditions, if you're going to have two more conditions, it means you're going to have four conditions. Right? So, I would suggest to you that in doing such questions in the exam, the first thing you need to look out for is how many questions or how many sub questions are based on the question. Right? In such a problem, you would identify you have two questions based on this, meaning, right, you are going to have four conditions because you know you have the first and second condition being fixed, right? So two questions means two more conditions after the second one, right? So third and fourth, right? It is important to identify that so that when drawing your table, you account for the two conditions. Again, this table is very important, right? Make sure you draw this table first thing when approaching these problems, right? So in drawing the table, I'm suggesting to you that you first identify or you first look at how many questions, right, you have based on this problem. That way you can know how many conditions you can expect, right? Hence you account for them. Are we clear?
Yes.
Right. Now, let us look at 3.1. Right. So you have the first and second condition. Right. Now let's look at questions. Right. Remember what I said about the first condition. To complete the first condition, you only need the number of teeth. If you noticed, we didn't even read the statement. Right. Now you would have to read this statement, right, so that you can get the number of teeth of each of the gears. Right. But in completing the first condition, you would only read the statement, right, to get the number of teeth of each of the gears. Right. And then when it comes to the questions based on the problem you're looking at, right, in most cases, you have to read the statement because sometimes or in most cases, they give you information that is crucial, right, for both of these questions. Right. Now, conditions that follow after the second condition, like in this case, condition 3 and 4, right? To complete a condition, right? So to complete a condition after the second condition, you need three things, right? You need two assumptions and the one unknown, right? You need three things. You need the unknown and two assumptions, right? Now, the two assumptions can sometimes be given in the statement, or sometimes you can be given one assumption in the statement, and then the second assumption you get in the sub question, which is the case for this problem, right? If you look at 3.1, they say calculate the speed and direction of the analysis. So out of the three things that you need to complete, right, to complete a condition, you already have one, which is what you're looking for. So you're looking for the rotational frequency of gear A, right? If the arm E is fixed, so they've given you one assumption. They said arm E is fixed. If arm E is fixed, it means the arm is not rotating, right? So at the moment, you have two things. If what you're looking for, the rotational frequency and direction of rotation of gear A, they've given you one assumption, which is arm E is fixed, so arm E is zero, or the rotational frequency of arm E is zero. So you need one more assumption, which you will get in the statement for sure. Right. So reading the statement, the epicyclic gear train shown in figure 3 consists of an analysis having 100 teeth, sun gear B connected with or connected to the output shaft having 28 teeth and rotating at 140 reps per minute. Right. Right. No need to continue reading the statement because we already have the third assumption. Right. They said the sun gear B connected to the output shaft having this many teeth and rotating at 140 reps per minute in a clockwise direction. Right. So that's the third assumption. Third assumption, right, is that gear B is rotating at 140 reps per minute clockwise. So that's the third assumption. Right. So now you have everything you need to complete the third condition. Right. The third condition, right, they said that the sun gear B is rotating at 140 reps per minute clockwise, hence the positive 140. So the positive 140 is an indication that gear B is rotating at 140 reps per minute clockwise. We are looking for gear A, the analysis, and they said the arm E is fixed, hence NE is equal to zero. So now you complete your third condition. They said this arm E is zero. They said we are looking for the rotational frequency of A, hence NA is, hence the question mark. And then they said gear B is rotating at 140 reps per minute clockwise, hence the positive 140. Right? Once the condition is complete, right, to get what you are looking for, right, you have to equate the second condition with your current condition. So the current condition is condition 3, right? So we are going to equate the second condition with the third condition, right? So we do that to formulate to formulate equations, which we will then solve simultaneously to get what we are looking for. Right. So again, to get what you are looking for, you equate the second condition to your current condition. That's where you formulate equations which will then solve simultaneously. Right. So essentially, we'll say y is equal to 0, and then take that as our first equation. X plus y is equal to NA. Take that as our second equation. And then our third equation will be negative 4,911 x plus y is equal to positive 140, right? Which is what I did here. So essentially, we have formulated three equations, right? From equating the second condition to the current condition, right? We got three equations out of it, right? Now, next, you identify what it is you're looking for. Once you've formulated the three equations, or once you've formulated your equations, you then look at what you're looking for. We're looking for NA. To get NA, you need both X and Y, right? Now, from our equations, we just so happen that we already have the value for Y. So Y is equal to 0. So we already have Y is equal to 0. So now we need to get X. Once we get X, then we substitute both here to get NA. Right? So all you do is you substitute this equation into the third equation. Right? Y is equal to 0. Right? Hence, you'll only be left with negative 4,911 plus 0 is equal to 140. Right, and then from this, we're looking for x. Therefore, you divide both sides by the negative 4,911. That is how this and that cancelled. Right, and then to get x, you simply say 140 divided by this. Punching this in our calculators, x, or the value of x, becomes this here. Right, so x is equal to negative 28,507. Right, now in this question, they did make a mistake. In the statement, they said gear B is rotating at 140. Right, they told us that the output shaft is rotating at 140. Right, so the output shaft is fitted to gear B. So if the output shaft is rotating at 140 revs per minute clockwise, it means gear B is rotating at 140 revs per minute clockwise. But then in figure 3, they said the output shaft is rotating at 120. Right, this is the mistake the examiner made. Right, so what we tend to do in the exam, or what we tend to do when marking, right, is we consider both 140 and 120. Right, so if you happen to write 120 here instead of 140, right, if everything you did is correct, then you'll be marked correctly. Right, because this is not a mistake by the students, but one by the examiner. So we would consider answers for both 140 and 120. Right, but I would suggest to you to always use information that is in the statement. Right, right, so we get the value of x. So once you have the value of x, you simply go back to this equation, substitute the value of x and y, and then you will get na. Right, so x is equal to this, then you add y, y is equal to 0. Right, so na essentially is equal to negative 28,507. Now you do not leave your answers here. Right, remember this indicates the direction of rotation. Right, so after writing this, you then say na is equal to 28,507 revs per minute anti-clockwise. This means that this is going anti-clockwise, and you have to indicate that in your final answer. Right, so you don't leave your answers as negative or just positive. You have to mention what the positive and negative means, of which negative means that this is rotating anti-clockwise, and had you gotten a positive answer, then that would mean that this is rotating clockwise. So positive means clockwise, negative means anti-clockwise. It's very important that part. Right? Don't leave your answers as just positive and negative. Always write down the direction of rotation. Are we clear here?
Yes, sir.
All right. Right, so that's 3.1. Right, 3.1 is complete. Now, once you get this, no need to go back to your table and writing this here. Right, as far as your table, once you've filled your table, right, you don't necessarily go back to it. Are we clear there?
Yes.
Right, now 3.2, which will fall under the fourth condition. Right, determine the speed and direction of arm E. All right, so remember, to complete condition 4, we need 3 things: what you're looking for, and 2 other assumptions. Right, determine the speed and direction of arm E. That's what you're looking for. So that's number 1. Assuming that the annulus is fixed. So that's the first assumption, that the annulus is fixed. So annulus is equal to 0. Right, and then again, the third you get from the statement. We already know from the statement that gear B is rotating by 140 revs per minute clockwise. All right, so you have the three things you're looking for in order to complete a condition, right? You have what you're looking for, which is NE, right? They're looking for the rotational frequency and direction of rotation of the arm, right? If gear A is fixed, that's the first assumption. And if gear B is rotating by 140 revs per minute clockwise, which makes a 3 or second assumption, hence you are able to complete your fourth condition, right? So in completing your fourth condition, we are looking for NE, hence the question mark here. They said the analysis is fixed, hence the 0, and then this remains the same. They said this is still positive 140, right? Now to get what you're looking for, you then equate your second condition to your current condition. So our current condition is condition 4. So you equate second condition with condition 4. Hence, your equations will be y is equal to NE, x plus y is equal to 0, negative 4,911x plus y is equal to positive 140. So again, you have three equations. Right, so from equating the second condition to the current condition, we get three conditions. I mean, we get three formulas or three equations, right? Now, from the three equations, you identify what you are looking for. We are looking for NE. To get NE, we need to get Y, the value of Y, right? So we do not necessarily need the value of X here. We just need the value of Y, right? So the quickest way to do this one would be to express X in terms of Y, so that in this equation, you'll only have one unknown, which will be Y, right? So you formulate a third equation, sorry, a fourth equation by expressing X in terms of Y. So you're going to take that side, hence X will be equal to negative Y. That you take as your fourth equation. Then now you substitute your fourth equation into the third equation. That way, X will be expressed in terms of Y, and you'll only have Y is the only unknown, right? So this times that is positive 4,911 Y. That plus Y gives us 5,911 Y, right? Is equal to, of course, the 140. And then we're looking for Y, so we divide both sides by the coefficient of Y here, which is 5,911. So you divide both sides by the 5,911. Then punching this in your calculators, this is what we get, right? So Y is equal to 23,685. That's the value of Y, right? So once we have the value of Y, we then go back to this equation, right? NE is equal to Y, hence NE is equal to Y being 23,685, right? Now this is positive, so this is 23,685 revs per minute. Because it's positive, it means it's going clockwise, right? So you don't just leave your answers as positive, you have to indicate direction of rotation, just like the question stipulated, right? The question was determine the speed and the direction, right? So direction would be clockwise or anti-clockwise, not just positive and negative. Are we clear here?
Yes.
Yes.
All right. And that is how you would attempt problems based on epicyclic gears. Very easy, very straightforward. Just follow those three easy steps and you should be fine. Any questions?
I no questions.
Right. Now, in determining this for your what is this for your first condition, right? This doesn't necessarily carry any marks, right? So you can either scribble it right on your question paper, right? Or maybe once you've drawn your table, right, you can write it here, right? But it doesn't necessarily carry any marks. You are just trying to establish this here. Right, when you guys do N5, hopefully you will have done this for quite a while. Hence, you won't necessarily need to do this. Right, so once you get used to it, it is very easy to work out in your head. Right, but for tomorrow, don't try working it out in your head. Right, make sure you write it down so that you get it right. Capiche? Hello.
Thank you. Bye.
No, what do I mean by we're not finished? We're not finished. I'm just asking if you guys get what the last thing I said. Do you understand what I'm saying?
Yes.
Yes.
All right. All right. So that is it as far as epicyclic gears. Right. Any and all problems you're going to approach like this. Right. This is probably the most complex one. This is probably the most complex problem and epicyclic gears. Other problems are pretty simple, right? Where you just have the annulus, and then you have the planetary gear, and then you have the sun gear. Right? You will take the very same approach, right? And then sometimes you have an epicyclic gear system where you have maybe a pinion and a gear wheel, right? Which are connected with an arm, right? And maybe they call this gear A and call this gear B. Very simple. You take the very same approach, right? Now with these ones, now with these kind of problems, because there is no clear analysis, right? For these kind of problems, because there is no clear analysis, right? Always choose the biggest gear in the system, right? It can be two gears, can be a number of gears, right? Either way. So by number of gears, I mean there could be a gear C here, right? There could be a gear C here, right? So this would be gear C, right? Connected with the arm. Now this here, the blue line represents the arm. So all these gears would be connected with this arm, making this an epicyclic gear system, right? So the biggest gear in the system, that is the one you use as your analysis. To make things easier for you, right? To make things easy, always go with the biggest gear in the system for such cases, right? So for such cases where you have um, a pinion and then you have two gear wheels, right? Connected with an arm, making this an epicyclic gear train, right? Always choose the biggest gear in the system as your analysis. So, for instance, here you would say fix the arm, say the arm is E again. So, fix the arm E and rotate, and then you would have gear C here. Rotate gear C by one revolution clockwise. So, biggest gear C being the biggest gear in the system, right? You would choose as your analysis. And then you follow the very same steps, right? So you'd have gear C here. Gear C is meshing with B, so you'd have gear B here. B is meshing with A, so you'd have A here. And then you follow those three easy steps, right? This will be 0, this will be 1, you'll have gear C here. And then you'll have gear B here, you'll have gear A here, right? And then in filling out the two columns, you use those three simple steps. Identify the relationship between the two gears, right? So gear B is meshing with C, so they have the same what is the circumferential velocity, right? Hence, NB TB will be equal to NC TC, right? This from condition one, since you've called this your annulus, so this is being rotated by one revolution clockwise. So this is going clockwise, right? Now, take note that these gears are measuring with the outside true circumference, meaning that they are going in different directions. So if this is going clockwise, it means this is going anti-clockwise. That's your second step, establishing direction of rotation, right? And since this is going clockwise, it means this is going anti-clockwise. Then you establish or you solve for what you're looking for. Third step, which you will then get what you're looking for here. Then you go to gear. So this will be gear A, right? Gear A is meshing with B, right? Gear A is meshing with B, at which point you follow the very same steps. So in following those steps, you then say the relationship between A and B is that NA is equal to NB times TB, right? Now you've identified or you've established the relationship between the two gears. Next, direction of rotation, right? Now direction of rotation is, you've already established that this is going anti-clockwise, right? So this one will be negative. So if this is going anti-clockwise, it means this is going clockwise. So it remains positive. Second step. Third step, solve for what you're looking for. What you're looking for is NA. So you divide both sides by TA. Hence, this will be negative NB TB divided by TA. Right? Now remember, what will you have gotten here is negative. So this negative times this negative will cancel each other out. Hence, whatever you get here, right, will be positive. So don't be confused by that. You won't be confused as long as you follow these three easy steps. The steps are not conditional. You follow them exactly as they are. Are we clear?
Yes.
Right. So that is it as far as what is this? Epicyclic gears. Right. This is probably the most complex one. Every other problem based on epicyclic gears is pretty straightforward. Right. Right. Now let us look at belt drives. Right. Belt drive should be a quick one. I'll also send you those notes once we are done here. Belt drives. Now, belt drives will be about 5 marks in the exam. It will be about 5 marks in the exam, right? Right. So under gear drives, we essentially look at two types of belts, right? Two types of belts and two types of belt systems, right? First, looking at types of belts, you have the flat belt as well as the V belt, right? Now, it is important to identify the type of belt because of how we use tension ratios, right? So as far as tension ratios for a flat belt, it's T1 over T2 is equal to E to the exponent mu alpha, right? Now, T1 and T2, you should know by now at this level that T1 and T2 are the tensions on the belt, right? The tight side tension we denote as T1, and the slack side tension we denote as T2, right? And then mu is the coefficient of friction, and then this here, theta, is the angle of wrap or angle of contact, right? Of which the angle of contact has to be in radians. Why? Because essentially we are looking at rotational motion, right? We're looking at angular motion, right? Theta, being the angle of wrap, is essentially the angle at which the belt wraps around the pulley, right? So the pulley being circular, right, and the belt being in motion, right? That is why we say essentially we're looking at angular motion, right? So meaning theta, right? If you've been given theta in degrees, you have to convert it to radians. And the way we convert um, theta from degrees to radians is by simply dividing the angle in radians by 57.3. So if you've been given the angle in degrees, you divide it by 57.3, and what you get will be theta in radians. So the theta, angle of contact, we only use in radians. If you use it in degrees, it means you have no idea what you are doing here. It means you have absolutely no idea. All right, so make sure the angle theta you use in radians. Right? Now, the flat belt has this cross section. Right? This is the cross section of the flat belt. You have the width of the belt as well as its thickness. Right? So if it happens you've been given the width and thickness of the belt, to get its area, you simply use this formula here. Right? And then the second type of belt is the V belt. Now, as far as the tension ratio for calculating or for V belts, it's T1 over T2. So the left hand side for both types of belts is the same. The only difference is the right hand side. So for V belt, T1 over T2 is equal to e to the exponent mu alpha times cosec. I think in your formula sheet, the right hand side is written as this: e to the exponent mu theta times cosec beta. Right? Now cosec is equal to 1 over sine. Right? We can't use this in our calculators. Right? That's why I express this side of the equation as e to the exponent mu theta divided by sine beta. Right? Mu and theta remain the same. Mu is still the coefficient of friction. Theta is still the angle of rep or angle of contact, which must be in radians. Right? The only new quantity here is this beta here. Right? Now this beta stands for half the V groove angle. Now this is the what is this the cross-sectional area of a V belt. Right? Now from precision measurement, you should know this by now, that this angle is known as the included angle. Right? So this angle here being the included angle, right, we know as the V groove angle. Right? And if you look at beta, right, beta will be what? Will be half the V groove angle. That is why beta is known as half the V groove angle. Right? So meaning if you're dealing with a V belt and they've given you the V groove angle, right, you divided that V groove angle by 2 to get beta. Right? So it's very important that you are careful as to how they've given you beta. Right? Because sometimes they'll say half the V groove angle, which is beta, but sometimes they'll also say the V groove angle is such and such. Right? Now, beta, half the V groove angle, we use in terms of degrees, because essentially we're not looking at angular motion. Right? So beta is used in degrees, hence I said here. Right? So beta is used in degrees, theta is used in radians. Right? And then the area of a V belt you will be given. Right? Right. And then we get what we call centrifugal tension. Right? So as far as tension ratios, your tension ratios depend on how many tensions are we considering, or how many tensions we are going to consider in a problem. Right? So if you're only considering the slack side and side, meaning if you are not considering the centrifugal tension, right, then depending on if you're looking at a flat belt or V belt, these are the tension ratio formulas that you use, right? If you are going to consider, or if you are considering centrifugal tension, right, then our tension ratios change a bit, right? Instead of having for a flat belt T1 over T2, you instead have T1 minus TC over T2 minus TC. The right hand side remains the same when considering centrifugal tension. Right, we do the same thing with the V belt. Right, only the left hand side changes. Instead of T1 over T2, you have T1 minus TC divided by T2 minus TC. The right hand side also remains the same here. Right, now what is centrifugal tension? Right, say you have a pulley, right, and it's wrapped with a belt. As the pulley is going, or as far as the direction of rotation, it is going in that direction, hence this being the tight side. And then this, from the diagram, you can see that this has a bit of slack, hence I've labeled it as T2. Now, centrifugal tension is the tension. Now, if you look at T1, if the belt is going in that direction, right, before the belt or before the motion reaches, what is this, reaches the where the belt wraps around the pulley, right, the motion is essentially linear, right? And then when it gets to this point, the motion changes all of a sudden, right? Now, centrifugal tension is that tension that tries to, how can I put this? That tries to resist this sudden change of motion. So, TC centrifugal tension is essentially trying to continue going on this trajectory, right? It doesn't want to, it's trying to resist this sudden change in motion, right? So that is what essentially um, what is this centrifugal tension is, right? And then centrifugal tension is equal to m dash times v squared. Now this here is the speed of the belt, right? Also known as the circumferential velocity of the belt, right? And then this is the mass of the belt per meter length of the belt. So meaning, oh, I should have wrote it here. So m dash is the mass of belt per meter length of the belt. So meaning it will be in kg per meter. Right, and then V, as you know by now, is equal to pi dn. Right. Now all of these tensions, right? Okay, before we get to that, sometimes we or you are given problems where they've considered the thickness of the belt. So by consider thickness of the belt, I mean if you are given the thickness of the belt, right? So in the problem statement, if they've given you the thickness of the belt, it means the thickness of the belt has been considered. And if the thickness of the belt has been considered, right, the way that affects our formulas is in terms of the diameter, right? So V being equal to pi dn, right? So we use this if the thickness of the belt hasn't been considered, meaning if you haven't been given the thickness. If you've been given the thickness, it means you have to consider it. And in considering the thickness of the belt, we then use the effective diameter, right? So the effective diameter is equal to the diameter of the pulley plus the thickness of the belt. So that's how the thickness of the belt, or considering the thickness of the belt, that's how it influences our formulas, right? So instead of just using the diameter of the pulley, we instead use the effective diameter being the diameter of the pulley plus the thickness of the belt. Right? Now, all of this is important in calculating the power being transmitted by the belt. Right? The formula to calculate the power being transmitted by the belt is TE, which is the effective tension, times V. The V being pi dn. Right, now effective tension, I did mention when we were doing bearings that you get two types of tensions when dealing with belt drives. Right, if the belt is transmitting power or transmitting torque, then we use the, what is this? The dynamic load, which for belt drives is effective tension. Effective tension is equal to T1 minus T2. And then when the belt is not transmitting any power or torque, we use installation tension. Right. So if you have to calculate power, clear indication that the belt is transmitting torque or power. Hence, we always use effective tension. So effective tension is T1 minus T2, and then V, as you know, is pi dn. Right. And then if you're considering thickness, the D will instead be the effective diameter, which is equal to D plus the thickness. Right, and that is it. That is belt drives in a nutshell. Right, now maybe I should mention that there is a formula.
Sorry, sir.
Yes,
Can you please share those notes on WhatsApp?
as always, boy.
Thanks.
I'm trying to find this formula. Where is this thing? Okay, when I find it, I will. There we go. So, this formula here. Right, so this formula to calculate the length of the belt, this one. So formula number 27. Right, this is the formula you use to calculate the length of the belt. If you have to calculate the length of the belt, right? I just want to check something quickly. Belt drives. I just want to check something quickly here. Belt drives. Belt drives is model 6. Where's this thing? There we go. Right. So this is the formula I'm referring to. Right, because it happens sometimes that the question is based on having to calculate the length of the belt. Right. Now, I did mention that you get two types of belts, and then I mentioned that you get types of belt drive systems, but I didn't necessarily mention the types of belt drive systems. So the different types of belt drive systems, right? You have two essentially: the open belt drive system, as well as the crossed belt drive system. Right. Now, the formula to calculate the length of the belt is essentially this one, right? But now you see you have plus or minus here, right? So the plus or minus will depend on the kind of, what is this, belt drive system you are looking at, right? For an open belt drive system, right, you use minus here, right? For open belt drive system, this here will be minus, And then for a crossed belt drive system, this will be plus. Are we together here?
Yes, sir.
Right. And that is it as far as what is this belt drives. Belt drives is only 5 marks in the exam, right? It's 5 easy marks. Do not leave it, right? It's 5 very easy marks, right? It's a lot to cover for 5 marks, but it is what it is, right? Belt drives will cover in detail in N5. Hopefully, you guys will be doing N5 next trimester. Right, that is where belt drives actually gets more exciting. In N4, it's very basic, very boring. Right? Any questions?
No questions, sir.
Beautiful. Then we are done here. Good luck to you guys tomorrow.
I'm sorry,
Thank you so
sir.
much, sir.
What's the passing mark?
Don't worry about the first person mark. Go there and go there and get so the first question is based on module 1, 2, and 3. So the first question is 15%, right? So if you say 100 minus 15, that is what? 85%, right? Hello?
Yes.
Exactly. Go there and fight for 85%. That's it.
Yeah, because question one it's theory, so
Don't go there fighting for the bare minimum. Fight for 85 and you'll be fine.
okay, thank you.
All right, guys. All the best. Bye.
Bye. Hi, Sisendwin here.